Hello, and welcome to our course on differentiation. Today, we're going to lay the foundation for all of calculus by understanding the core concept of the derivative. By the end of this lesson, you will be able to define the derivative of a function as a limit, and you'll be able to calculate the derivative of a function using this limit definition. So what is a derivative? At its heart, a derivative is a measure of how a function changes. Think of it as the instantaneous rate of change. Imagine you're driving a car. Your average speed over a trip might be 60 miles per hour, but at any single moment, your speedometer shows your instantaneous speed. That instantaneous speed is a derivative. In mathematics, this idea of instantaneous rate of change is represented by the slope of a tangent line. Let's look at a graph of a function, f of x. If we pick a point on the curve, say at x equals a, the tangent line is the line that just touches the curve at that one point. The slope of this tangent line is the derivative of the function at that point. But how do we find the slope of a line that only touches the curve at one point? We can't use the standard slope formula, which requires 2 points. The solution is to use a secant line. A secant line connects 2 points on the curve. Let's pick our first point at x equals a, and a second point at x equals a plus h, where h is a small number. The slope of this secant line, which we'll call m sub secant, is the change in y divided by the change in x. That's f of a plus h minus f of a, all divided by a plus h minus a, which simplifies to h. Now here's the key idea. What happens if we make the second point closer and closer to the first point? In other words, what happens as h gets closer and closer to 0? As h approaches 0, the secant line becomes a better and better approximation of the tangent line. The slope of the secant line approaches the slope of the tangent line. This is where limits come in. The slope of the tangent line, which is the derivative, is the limit of the secant line slope as h approaches 0. This is the formal definition of the derivative. We denote the derivative of f of x as f prime of x. So f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x, all over h. This is the fundamental formula we'll be using. Let's recap. We've defined the derivative as the instantaneous rate of change, which is the slope of the tangent line. We found this slope by taking the limit of the slope of a secant line, as the 2 points on the secant line get infinitely close. This gives us our limit definition of the derivative. Now that we have the definition, let's put it into practice. In this scene, our objective is to calculate the derivative of a simple function using the limit definition. We will calculate the derivative of f of x equals x squared. Let's start by writing down our formula. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x, all over h. Our first step is to find f of x plus h. Since f of x is x squared, f of x plus h is simply x plus h squared. So f of x plus h equals x plus h squared. Now we substitute this into our limit formula. F prime of x equals the limit as h approaches 0 of the quantity x plus h squared minus x squared, all over h. If we try to plug in h equals 0 right now, we get 0 over 0, which is an indeterminate form. This means we need to simplify the expression first. Let's expand the numerator. X plus h squared is x squared plus 2xh plus h squared. So our expression becomes the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared, all over h. Notice that the x squared terms cancel out. This leaves us with the limit as h approaches 0 of 2xh plus h squared, all over h. Now we can factor out an h from the numerator. This gives us the limit as h approaches 0 of h times the quantity 2x plus h, all over h. Since h is approaching 0 but is not equal to 0, we can cancel the h in the numerator and the denominator. This simplifies to the limit as h approaches 0 of 2x plus h. Now we can finally substitute h equals 0. Plugging in h equals 0, we get 2x plus 0, which is just 2x. So the derivative of x squared is 2x. Let's recap. We successfully used the limit definition to find the derivative of x squared. The process involves substituting into the formula, simplifying the expression to avoid division by 0, and then evaluating the limit. We have now met our objective for this scene. Let's try another example. In this scene, we'll find the derivative of a linear function. Our objective is to calculate the derivative of f of x equals 3x plus 4 using the limit definition. Again, we start with our definition. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x, all over h. First, let's find f of x plus h. We replace every x in our function with x plus h. So f of x plus h equals 3 times the quantity x plus h plus 4. Distributing the 3, we get 3x plus 3h plus 4. Now we substitute this into our limit formula. F prime of x equals the limit as h approaches 0 of the quantity 3x plus 3h plus 4 minus the quantity 3x plus 4 all over h. Let's simplify the numerator. Be careful with the negative sign. The numerator becomes 3x plus 3h plus 4 minus 3x minus 4. The 3x terms cancel, and the 4 terms cancel. We are left with just 3h. Now we can cancel the h in the numerator and denominator. This leaves us with the limit as h approaches 0 of 3. The limit of a constant is just the constant itself. So the derivative of 3x plus 4 is 3. This result makes perfect sense. The function f of x equals 3x plus 4 is a straight line with a slope of 3. The derivative, which represents the slope of the tangent line, should be 3 everywhere on the line. We have successfully calculated the derivative of a linear function using the limit definition. For our final example using the limit definition, let's tackle a slightly more complex function. Our objective is to calculate the derivative of f of x equals the square root of x plus 1. As always, we start with the definition. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. First, let's find f of x plus h. F of x plus h is the square root of x plus h plus 1. Now, substitute this into our limit formula. F prime of x equals the limit as h approaches 0 of the square root of x plus h plus 1 minus the square root of x plus 1 all over h. Again, plugging in h equals 0 gives us 0 over 0. When you have a limit with square roots in the numerator, a common technique is to multiply by the conjugate. The conjugate of the numerator is the square root of x plus h plus 1 plus the square root of x plus 1. We multiply both the numerator and the denominator by this conjugate. Remember the difference of squares formula. a plus b, equals a squared, b squared. Here, a is the first square root and b is the second. So the numerator becomes the quantity x plus h plus 1 minus the quantity x plus 1. The square roots disappear. Let's simplify the numerator. X plus h plus 1 minus x minus 1. The x's cancel and the 1's cancel, leaving us with just h. Now, let's rewrite our limit with the simplified numerator. F prime of x equals the limit as h approaches 0 of h, all over h, times the quantity square root of x plus h plus 1, plus square root of x plus 1. We can now cancel the h in the numerator and denominator. This leaves us with the limit as h approaches 0 of 1, all over the square root of x plus h plus 1, plus the square root of x plus 1. Finally, we can substitute h equals 0. This gives us 1 over the square root of x plus 1, plus the square root of x plus 1, which simplifies to 1 over 2 times the square root of x plus 1. We have successfully found the derivative of the square root function. As you can see, using the limit definition can be quite tedious. Thankfully, mathematicians have developed a set of rules that allow us to find derivatives much more quickly. In this lesson, we'll learn the most basic of these rules. Our objective is to learn and apply the constant, power constant multiple, and sum/difference rules of differentiation. Let's start with the simplest rule. The constant rule states that the derivative of any constant is 0. If f of x equals c, where c is any real number, then its derivative, f prime of x, is 0. Why is this true? Think about the graph of a constant function, like f of x equals 5. It's a horizontal line. The slope of a horizontal line is always 0. Since the derivative is the slope of the tangent line, and the tangent line to a horizontal line is the line itself, the derivative must be 0. For example, if f of x equals 7, its derivative is 0. If g of x equals negative 100, its derivative is 0. If h of x equals pi, its derivative is 0. Any constant, its derivative is 0. Next up is the most important rule for differentiating polynomials. The power rule states that if f of x equals x to the power of n, then its derivative is n times x to the power of n minus 1. In other words, you bring the exponent down as a coefficient and then subtract 1 from the exponent. Let's see this in action. Remember our first example, f of x equals x squared? Using the power rule, we bring the 2 down and subtract 1 from the exponent. That gives us 2 times x to the power of 1, which is just 2x. This matches the result we got from the limit definition, but it was much faster. Let's try another one. If f of x equals x to the 5th power, its derivative is 5 times x to the power of 5 minus 1, which is 5x to the 4th. If f of x equals x, which is x to the 1st power, its derivative is 1 times x to the power of 1 minus 1, which is 1 times x to the 0, or just 1. This also makes sense, as the slope of the line y equals x is 1. The power rule works for any real number n, including negative and fractional exponents. For example, if f of x equals 1 over x, we can rewrite it as x to the negative 1. Using the power rule, the derivative is negative 1 times x to the power of negative 1 minus 1, which is negative 1 times x to the negative 2, or negative 1 over x squared. Similarly, if f of x equals the square root of x, we can write it as x to the 1/2 power. The derivative is 1/2 times x to the power of 1/2 minus 1, which is 1/2 times x to the negative 1/2, or 1 over 2 times the square root of x. This also matches our previous result. Now, let's combine the power rule with a constant. The constant multiple rule says that if you have a constant c multiplied by a function f of x, its derivative is the constant c times the derivative of the function. You can essentially pull the constant out of the differentiation process. For example, if f of x equals 5x cubed, the derivative is 5 times the derivative of x cubed. The derivative of x cubed is 3x squared. So the final answer is 5 times 3x squared, which is 15x squared. Finally, let's see how to differentiate functions that are sums or differences of other functions. The sum and difference rules state that the derivative of a sum or difference of functions is the sum or difference of their derivatives. You can differentiate each term separately. Let's put it all together with a polynomial. If f of x equals 4x cubed minus 2x squared plus 7x minus 10, we can differentiate each term. The derivative of 4x cubed is 12x squared. The derivative of negative 2x squared is negative 4x. The derivative of 7x is 7. And the derivative of negative 10 is 0. So the final derivative is 12x squared minus 4x plus 7. We have now learned and applied the constant, power, constant multiple, and sum/difference rules. These rules are the building blocks for differentiating more complex functions. So far, we've learned how to differentiate sums and differences of functions. But what about products? In this lesson, we'll learn a new rule for that. Our objective is to understand and apply the product rule to differentiate functions that are the product of two other functions. A common mistake is to think that the derivative of a product is just the product of the derivatives. Let's see why that's wrong. Consider the function f of x equals x squared. We know its derivative is 2x. But we can also write x squared as the product of two functions, x times x. Let's call them u of x equals x and v of x equals x. The derivative of u is 1, and the derivative of v is also 1. If we were to just multiply the derivatives, we would get 1 times 1, which is 1. But we know the correct answer is 2x. Since 1 is not equal to 2x, the product of the derivatives is not the derivative of the product. We need a special rule. This is the product rule. If f of x is the product of two functions, u of x and v of x, then its derivative is the derivative of the first function times the second function, plus the first function times the derivative of the second function. A common way to remember this is first times derivative of second plus second times derivative of first. Let's apply this to our example. F of x equals x squared. We have u equals x and v equals x. so u prime is 1, and v prime is 1. Using the product rule, f prime of x equals 1 times x plus x times 1, which is x plus x, or 2x. This matches our known result. The product rule works. Let's try a more complex example. Let's find the derivative of f of x equals the quantity x squared plus 3x times the quantity 4x minus 5. First, identify u and v. Let u of x be the first part, x squared plus 3x. Let v of x be the second part, 4x minus 5. Next, find their derivatives. Using the power and sum rules, u prime of x is 2x plus 3. The derivative of v of x is 4. Now, plug everything into the product rule formula. F prime of x equals u prime times v plus u times versus prime. That's the quantity 2x plus 3 times the quantity 4x minus 5 plus the quantity x squared plus 3x times 4. The final step is to simplify by expanding and combining like terms. Expanding the first part gives 8x squared minus 10x plus 12x minus 15. Expanding the second part gives 4x squared plus 12x. Combining the x squared terms, we get 12x squared. Combining the x terms, we get 14x. And we have the constant term, negative 15. So the final derivative is 12x squared plus 14x minus 15. We have now successfully used the product rule to differentiate a function. Remember, the key is to identify the two functions being multiplied, find their individual derivatives, and then apply the formula. Just as we needed a rule for products, we also need one for quotients. In this lesson, we'll learn the quotient rule. Our objective is to understand and apply the quotient rule to differentiate functions that are the quotient of two other functions. The quotient rule is a bit more complicated than the product rule, but it follows a clear pattern. If f of x is the quotient of two functions, u of x divided by v of x, then its derivative is the derivative of the top function times the bottom function minus the top function times the derivative of the bottom function, all divided by the bottom function squared. A common mnemonic is low d high minus high d low, all over low squared. Let's break that down. Low refers to the denominator v of x. High refers to the numerator u of x. D high means the derivative of the numerator u prime of x. And d low means the derivative of the denominator v prime of x. Let's try an example. Let's find the derivative of f of x equals the quantity x squared plus 1 divided by the quantity 3x minus 2. First, identify the high and low functions. The numerator, u of x, is x squared plus 1. The denominator, v of x, is 3x minus 2. Next, find their derivatives. The derivative of u prime of x, is 2x. The derivative of v prime of x, is 3. Now, plug everything into the quotient rule formula, low d high minus high d low, all over low squared. F prime of x equals the quantity 3x minus 2 times 2x minus the quantity x squared plus 1 times 3, all divided by the quantity 3x minus 2 squared. Finally, simplify the numerator. We usually leave the denominator in its squared form. Expanding the numerator, we get 6x squared minus 4x minus the quantity 3x squared plus 3. Distributing the negative sign, we get 6x squared minus 4x minus 3x squared minus 3. Combining like terms, the numerator simplifies to 3x squared minus 4x minus 3. So the final derivative is 3x squared minus 4x minus 3, all over the quantity 3x minus 2 squared. Let's try one more example to solidify the process. Find the derivative of f of x equals 5x over x squared plus 4. Here, u is 5x, so u prime is 5. And v is x squared plus 4, so v prime is 2x. Applying the rule, we get 5 times the quantity x squared plus 4 minus 5x times 2x, all over the quantity x squared plus 4 squared. Simplifying the numerator, we get 5x squared plus 20 minus 10x squared, which is negative 5x squared plus 20. So the derivative is negative 5x squared plus 20, all over the quantity x squared plus 4 squared. We have now successfully applied the quotient rule. Remember the mnemonic, low d high minus high d low, all over low squared, to help you recall the formula. We've learned how to differentiate sums, differences, products, and quotients. But what about composite functions, like the square root of x squared plus 1, or sine of x cubed? For these, we need the chain rule. Our objective is to understand and apply the chain rule to differentiate composite functions. A composite function is a function inside another function. We can think of it as an outer function and an inner function. For example, in the function f of x equals the quantity 3x plus 2 to the fifth power, the outer function is something to the fifth power, and the inner function is 3x plus 2. The chain rule states that the derivative of a composite function is the derivative of the outer function, evaluated at the inner function, times the derivative of the inner function. In simpler terms, it's the derivative of the outside times the derivative of the inside. Let's apply this to our example. F of x equals the quantity 3x plus 2 to the fifth power. The outer function is u to the fifth, and its derivative is 5u to the fourth. The inner function is 3x plus 2, and its derivative is 3. Now we apply the rule, derivative of the outside times the derivative of the inside. The derivative of the outside is 5u to the fourth. We evaluate this at the inner function, 3x plus 2, so we get 5 times the quantity 3x plus 2 to the fourth. Then we multiply by the derivative of the inside, which is 3. So the final answer is 5 times the quantity 3x plus 2 to the fourth times 3, which simplifies to 15 times the quantity 3x plus 2 to the fourth. Let's try an example with the trigonometric function. Find the derivative of f of x equals sine of x squared. The outer function is sine of u, and its derivative is cosine of u. The inner function is x squared, and its derivative is 2x. Applying the chain rule, we get the derivative of the outside, cosine of u, evaluated at the inside, x squared, which is cosine of x squared. Then we multiply by the derivative of the inside, 2x. So the derivative is 2x times cosine of x squared. Finally, let's look at an exponential function. Find the derivative of f of x equals e to the power of 3x cubed plus 1. The outer function is e to the u, and its derivative is e to the u. The inner function is 3x cubed plus 1, and its derivative is 9x squared. Applying the chain rule, we get the derivative of the outside, e to the u, evaluated at the inside, 3x cubed plus 1, which is e to the power of 3x cubed plus 1. Then we multiply by the derivative of the inside, 9x squared. So the derivative is 9x squared times e to the power of 3x cubed plus 1. We have now learned and applied the chain rule. The key is to identify the outer and inner functions, differentiate them separately, and then multiply the results, making sure to evaluate the outer derivative at the original inner function. Let's recap what we've learned in this course on differentiation. We started with the fundamental definition of the derivative as the limit of the slope of a secant line. This gives us the instantaneous rate of change of a function. We then moved on to the basic rules that make differentiation much more efficient. The constant rule, the power rule, the constant multiple rule, and the sum and difference rules. Next, we learned how to handle products and quotients of functions with the product rule and the quotient rule. We saw why these special rules are necessary and how to apply them. Finally, we tackled composite functions with the chain rule, which is essential for differentiating functions like sine of x squared or e to the power of 3x cubed plus 1. You now have a solid foundation in the core concepts and rules of differentiation. The key to mastering these is practice. Work through the examples again and try the practice problems provided. The more you practice, the more intuitive these rules will become. Thank you for watching.